and a little ball. But the ball, it just doesn't have enough energy, enough oomph to get over the top.
Right. In our everyday world, classical physics is very clear.
Yeah, it's stuck. It'll roll back down, maybe sideways, but it's absolutely not getting over that hill unless you give it a big push.
The energy barrier is, well, a barrier. Insufficient energy means you're staying put. Simple as that, classically speaking.
Exactly. Feels like common sense. But then there's the quantum world. And what if, just completely ignoring that common sense, the ball could suddenly, phase through the hill?
Poof, appears on the other side.
Without ever going over. That's what we're diving into today, quantum tunneling.
It's one of the truly non-intuitive quantum effects.
So welcome to this deep dive. We're going to unpack this really strange phenomenon using the source material you've looked at. Our mission really is to explore how quantum uncertainty, specifically this link between energy and time, actually allows this tunneling to happen.
And it's not just a weird theoretical idea. We'll see. It has some, well, pretty significant real-world consequences.
Okay, let's ground ourselves first, like the source does.
Yeah.
The classical picture. Think about an alpha particle that's, 2 protons, 2 neutrons?
Correct. A little helium nucleus, essentially. And it's inside a big atomic nucleus, maybe uranium.
And inside, it's held tight by the strong nuclear force. That's the glue.
A very strong glue. But all the protons in the nucleus are positively charged, and they repel each other electromagnetically.
Right. Opposites attract, likes repel. So that repulsion creates an energy hill around the alpha particle.
Precisely. We call it the Coulomb barrier. It's an electrostatic energy barrier it has to overcome to get out.
But the energy the alpha particle has is less than the height of that barrier. So classically, trapped forever.
Classically, yes. It should just bounce around inside indefinitely. No escape route.
Okay, so that's the dead end in the classical world. Now let's jump into the quantum rules. And Heisenberg's uncertainty principle is, fundamental here, isn't it?
Absolutely central. And it's crucial to understand. It's not about having bad measuring tools. It's inherent to nature.
Yeah, it's not just fuzziness because we're clumsy.
No. It's baked in.
Oof.
There are pairs of properties, like position and momentum, where the more precisely you know one, the less precisely you inherently know the other.
Okay. But for tunneling, the key pair is energy and time, you said.
That's the one. The principle states E multiplied by E is greater than or equal to a tiny constant, Planck's constant divided by 4 or E.
So ito is the uncertainty in energy, the uncertainty in time.
Exactly. And it's just a very, very small number, which is why we don't see these effects easily in our large-scale world.
What does that relation mean, though, for energy and time?
It means if you consider an extremely short interval of time a really tiny instant, then the uncertainty in the particle's energy has to be large.
Ah, so its energy isn't perfectly fixed over that tiny instant. It's fuzzy.
Fuzzy is a good way to put it. It's indeterminate. There's an inherent range of possible energies it could have for that fleeting moment.
Okay, so this fuzziness, this is the key. How does that lead to tunneling? This is where the spontaneous energy fluctuations come in.
Yes, exactly. The energy-time uncertainty relation actually permits these fluctuations. The particle's energy can sort of deviate from its average value, but only for that very short time dictated by the uncertainty principle.
The source used that energy loan analogy, which I thought was helpful.
It's a great analogy. The universe allows the particle to briefly borrow an amount of energy, but that loan has to be repaid incredibly quickly within the time it.
The bigger the loan, the faster it needs paying back.
Precisely. And importantly, this isn't actually violating energy conservation in the grand scheme of things. It's just how energy behaves at these quantum timescales. It has this inherent indeterminacy.
Okay, I think with you. Particle stuck behind the barrier, its energy is fluctuating because of uncertainty. How does that get it through?
Right. So the particle is constantly, probing the barrier, bumping up against it.
Billions of times a second, probably.
Right. Easily. Now, during one of those incredibly brief moments where its energy fluctuates upwards, takes out that energy loan, its energy might momentarily equal or even exceed the height of the barrier.
Ah, okay. So for just an instant, it has enough energy.
Effectively, yes. For that tiny day allowed by the uncertainty principle, its energy state is consistent with being able to overcome the barrier. And in that same instant, because quantum mechanics is probabilistic,
there's a chance it's found somewhere else.
There's a non-zero probability of finding the particle on the other side of the barrier. It's not that it climbed over in that instant. It's more like the barrier temporarily ceased to be an absolute obstacle because of the energy fluctuation.
So it exploits the fuzziness, it borrows the energy, finds
Yep.
itself on the other side, and
And the
then...
loan is instantly repaid. Its
Mhm.
energy drops back down to its original lower value. But it's already through. It tunneled.
Wow. Yeah, that's deeply weird. It didn't go over, it just sort of peered past it.
It went through, exploiting that temporary quantum allowance.
And the chance of this happening for any one particle, any one attempt, must be tiny.
It's extremely small, usually. But, as you said, particles are constantly interacting with barriers. With enough particles or enough time, that tiny probability becomes a certainty. Something will tunnel eventually.
And the source mentioned things that affects that probability, like
Yeah.
the barrier itself.
Yes. The probability drops dramatically if the barrier is higher. Makes sense. You need a bigger energy loan.
Okay.
It also drops if the barrier is wider. The particle has to effectively traverse more forbidden space.
Right, longer distance.
And also, the mass of the particle matters. Heavier particles tunnel much less easily than lighter ones, like electrons.
Okay, that's one way to picture it with the energy loan. But there's another perspective too, right? Using the wave function.
Yes, thinking about quantum particles as waves, described by a wave function, offers another powerful insight. The wave function tells you the probability of finding the particle somewhere.
Okay.
So imagine the particle's wave approaching the barrier instead of just stopping flat, hitting a wall.
It doesn't.
No. The wave function actually penetrates into the barrier. Its amplitude decreases exponentially inside the barrier region.
So it gets weaker and weaker the further in it goes.
Exactly. But, and this is the key, if the barrier isn't infinitely thick,
Which real barriers aren't.
right, then the wave function, even after decaying through the barrier, will still have a tiny but non-zero amplitude on the other side.
And the amplitude squared gives the probability.
Meaning there's a non-zero probability of finding the particle on the far side. It is tunneled through.
So the wave picture gives the same result tunneling as possible.
It does. And fundamentally, the energy-time uncertainty principle is what underpins why that wave function doesn't just vanish at the barrier, why it has this possibility of extending through.
Okay, two ways to think about it. And alpha decay, back to our uranium atom, that's like the classic real-world proof.
It's the textbook example, yes. Those alpha particles inside the nucleus, as we said, are trapped by the Coulomb barrier. Classically, they lack the energy to get out.
But uranium is radioactive. Those alpha particles do get out.
They tunnel out. There's that small, constant probability for any given alpha particle to tunnel through the barrier in any given second.
And that explains why radioactive decay is probabilistic. You can't say when a specific nucleus will decay, just the odds over time, the half-life.
Exactly. The half-life is basically a measure of how long you have to wait, on average, for that tunneling probability to add up significantly.
Okay, let's try and wrap this up then. Key takeaways. Quantum tunneling. It's real. Particles can pass through barriers they don't have the energy to climb over.
And the mechanism behind it is quantum indeterminacy, specifically, the energy-time uncertainty principle,
Which allows these fleeting energy fluctuations, the energy loans.
giving the particle a momentary chance to bypass or exist beyond the barrier.
Or, thinking in waves, the particle's probability, its wave function, leaks through the barrier.
Leading to a finite chance of finding it on the other side.
I mean, you mentioned this isn't just, weird physics for physicists. It's vital for stars.
Absolutely. Nuclear fusion in the sun relies on protons tunneling through their mutual electrical repulsion to get close enough to fuse. Without tunneling, the sun wouldn't shine.
Wow. And modern electronics, too.
Many semiconductor devices, like tunnel diodes and the operation of flash memory, depend critically on electrons tunneling through thin insulating layers. It's happening in your phone right now.
So it's everywhere, just hidden from our direct view.
Pretty much. It really underscores how different the rules are at the quantum level.
Yeah, the source finished by calling tunneling this remarkable leap of faith at the subatomic level, enabled by the universe's inherent fuzziness.
That inherent uncertainty, that lack of perfect definition at the quantum scale, isn't just a limitation. It actually enables phenomena like this.
Makes you wonder, doesn't it? What does it really mean for reality to be fundamentally indeterminate, not set in stone?
What other possibilities does that fuzziness allow? It's kind of the power of uncertainty, as the source puts it. Definitely something to think about.